All right, now we're recording. So P of 0 is 0, P prime is 1 over 1 plus x, that's 1. P double prime, negative 1 over 1 plus x squared, that's negative 1. Okay, what's P triple prime? Well, what's the function itself? Just so we have it. Should be 2 over 1 plus x cubed. Yeah. Which should give us 2. Yeah. And then the next one, the fourth derivative, what do we get with that one? Yeah, negative 6 over 1 plus x to the fourth. You must have put yours into a online integral calculator or derivative calculator. Oh, okay, your own calculator. Okay. And that should have given us negative 6. So everybody agree with that? Everybody agree with that at home? Are you guys good with that at home?
Yep.
Yeah. Great. So then we would just set up our polynomials. We want a fourth degree polynomial. So that means we have to go up until we get to x to the fourth. We start with our first term 0 plus our next one is our coefficient on the x's of 1, so 1x. And that's over 1 factorial. And I should really put this as over 0 factorial. I won't write those every time, obviously, but for now. The next one is a minus 1x squared over 2 factorial. Then we have a plus 2x cubed over 3 factorial. And then we would have had a minus 6x to the fourth over 4 factorial. And we should be able to simplify that down. What should we get if we simplify that down? First term is just 0 over 1. My computer just made some weird noises. So that's just 0. We can get rid of that. Next term should just be x. Next term should be x squared over 2, then plus, and then minus x to the fourth over 4. And so that is our fourth degree Taylor polynomial that should represent the function natural log of 1 plus x at x equals 0. And we found a polynomial to represent natural log of, do we do for natural log of 1 plus x, or we do natural log of 1 minus x back a couple days ago? Anybody remember? We did 3 minus x. Yeah, I know we did that. A couple before that. I think it was the first one before the inverse tangent one, I believe. We did 1 plus x, right? And so and what was your series for 1 plus x? What did we come up with as our value? We had the sum from n equals negative 1 to the n, x to the n, right? And so we would note that effectively we're sort of looking at the same thing here, except that we're going to end up with a first term here that is a what? No, n equals 0 to infinity, negative 1 to the n, x to the n. The first term of this is, if we plug in 0, first term of that is, right, we end up with a 1, and then the second term is going to become a negative x and a plus x. This is not our series for natural log of 1 plus x. You told me the wrong thing, Noah. That's why. Yeah, I was going to say, you told me 1 over 1 plus x. There we go. There we go. Now, if we look at this series here, now it's going to be correct. If we plug in n equals 0, what do we get? We get x to the first over 1, which is x. We plug in n equals 1, we get minus x squared over 2. We plug in n equals 3, we get plus x cubed over 3 minus x to the fourth over 4. So when that this series is exactly the same as what we got using the Taylor polynomial, right? So you get the same form of this series. And so we should be able to note that if we extended this out forever, the same exact thing would continue to happen. We get plus x to the fifth over 5 minus x to the sixth over 6 and so on. And that either way that you do this, you're going to get the same thing, whether you integrate 1 over 1 plus x or whether you construct it using the Taylor polynomial or the Taylor series form. Good or no? Yes, you will be asked specifically to use Taylor series, yeah, and to write a Taylor series. All right. So let's see here. I was going to say that we should look at this one, but we already looked at this one on the graph a couple days ago. So we call this the Taylor polynomial. If we write out the entire series, like I said, we call it the Taylor series. This is a Taylor series that is centered at 0. And the more terms of it that we put in, the better the approximation at 0 will become. And in addition to that, there is a specific name for a Taylor series that is centered at 0. A Taylor series that is centered at 0 is called a Maclaurin series. Maclaurin series. This is a Taylor series at 0. And I may have this later on in the notes today, but I mention it now. A Maclaurin series is a Taylor series at 0. An important thing to note, because sometimes on the AP test in the free response questions, they will specifically say a Maclaurin series, and then they won't tell you where to center it. And so you'll need to know that a Maclaurin series is just a Taylor series at 0. Everybody good there? Zoom good there? Okay.
Yeah.
We're going to talk about what happens if we move it away from 0 in a little bit. But before we do that, I want to take a look at a couple of pretty cool little cases here that we're going to see. So we're going to construct a 7th order or 7th degree. You might see either one, 7th order or 7th degree Taylor polynomial, and then figure out the Taylor series for sine of x at x equals 0. So what are our steps going to be for this? What do we need to do first? Get the what? Get the derivatives. We got to find sine of 0, and then the derivative of sine at 0, and then the second derivative of sine at 0, and the third derivative of sine at 0, and the fourth derivative, and the fifth derivative, and so on. Okay. So first off, what is the sine of 0? What? 0. What is the derivative of sine? It is cosine. So what's the cosine of 0? What's the derivative of cosine? Negative sine. Negative sine of 0 ought to be. Right, what's the derivative of negative sine? Ought to be negative cosine. What's the negative cosine of 0? Negative 1. What's the derivative of negative cosine? Sine. That's going to be 0 again. We'll note that these are just going to repeat over and over and over and over and over and over again as many times as we need them to. That looks like that's the right number of times. Right? This is our original function. So this is not a derivative. This is our first derivative, our second derivative, third, fourth, fifth, sixth, seventh derivative. If we want a 7th degree or a 7th order Taylor polynomial, we want to have 7 derivatives, because that's going to give us our x to the 7th term. So let's write this out. First thing we should have is 0 x to the 0 over 0 factorial, right? Next thing we should have is plus 1 x to the first over 1 factorial. Next thing we should have is zero x squared over 2 factorial minus 1x cubed or x cubed over 3 factorial. Then zero x to the 4th over 4 factorial. Then and another 0x to the 6th over 6 factorial, and then a minus x to the 7th over 7 factorial. Everybody agree with that? Fairly straightforward to construct the polynomial. Find the derivatives. These were easy derivatives to find. Find the derivatives, plug in the things. All right, all the ones with the zeros are going to cancel out, so we can ignore all of those. So effectively, we just end up with x minus x cubed over 3 factorial plus x to the, that's not a plus sign, let's try again, plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Everybody good there? All right. What do you think the next term would be if we wanted to continue further than that? Plus x to the 9th over 9 factorial, then a minus x to the 11th over 11 factorial, and so on. Can we come up with a series notation, a summation notation to represent the full Taylor series for sine of x? See if you guys, take a second, see if you guys can come up with something. A sum from n equals 0 to infinity of something that will model this perfectly for each of these terms, knowing what they need to continue doing, swapping back and forth to x to the 9th over 9 as a positive, and x to the 11th over 11 factorial as a negative, and so on. What's the first thing we know it's going to have? It's going to have a negative 1 to some power. Does n work? Right, so n equals 0 is not going to matter, right? Because we know we're not going to have n equals 0 is got to be positive, right? And that's going to give us positive 1 for our first term, and then n equals 1 is going to give us negative, right? So that's fine. Okay, so then what? All right, Noah here in class says x to the 2n plus 1. Does that work out for our, if we plug in n equals 0, that's going to give us our first term there is x to the first. That's good, right? And then the next term will be an x to the third if we plug in 1, and then an x to the fifth, and an x to the seventh, right? So the plus 1 starts us at a power of 1, and the 2n makes it skip by 1 each time. Right? And then over 2n plus 1 factorial. Everybody at home good with that? Same concept. We have a 1 factorial underneath the x, which is our 0 plus 1, and then we have a 3 factorial, 5 factorial, and so on. Everybody good there?
Yeah.
Wonderful. All right. So, sine of x. A sum from n equals 0 to 1. We'll just start at 1. What do we have? We have negative 1 to the n, and we have x to the 2n plus 1, and we have divided by 2n plus 1 factorial. And we'll note that just with going from 0 to 1, that would be just those first two terms, right? X minus the x cubed over 3 factorial. It already starts to look like sine a little bit, right? Just around 0. Suppose we added in another one. Looks like sine for a little further, right? Suppose we made it 5. It matches up really nicely with sine for a little bit further. Suppose we put in, well, 19. I meant to hit 10. I meant to hit 10. 10. It matches up even further, right? Put in 20.
We can't see. Are you on Desmos right now? Because we can't see it.
I didn't share it with you guys. Never mind. All right, we're gonna start over. 3 of you really got that. We're like really impressed. There we go. N equals 1. Try this again. My bad, everybody. Y'all see the screen now on Desmos?
Yeah, we're good now.
All right. N equals 1. It matches up pretty well around 0, doesn't it? Looks like sine. Up to 2 matches up a little bit better. Up to 3, even better. To 4, even better. To 5, even further. What if we made it 10? Look how good that looks at 10. Isn't that kind of amazing, really? What if we made it 15? As far as I can see, it looks perfect. And now if we zoom out, we'll let it. Okay, we can see when we zoom out, it still deviates away eventually, right? What if I did 25? Give it a second here. Look at that. looks really good, doesn't it? When's it going to stop looking perfect? I mean, yeah, around 20 for this one, but like in general, if I were to continue going up towards infinity, where do you think it's going to stop looking perfect? Let's see if it can handle 50. It has a lot of trouble. I know we were slow before without the factorials. As soon as you put the factorials in it, you can see it's like, it's having some trouble here now. Did you guys see what does it look like this might converge for? If I went high enough, I'm only at 50. If I went towards infinity, probably it should converge for all real numbers from negative infinity to infinity. Isn't that cool? We can take, and all this is a polynomial. You guys realize that, right? All this is a polynomial. It's x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over whatever 7 factorial is, and so on, all the way out, extended 50 terms, well, 51 terms, 0 to 50, right? And it matches up with sine x and is identical to sine x for, in this case, negative, 35 or so to 35. But if we went to infinity for our n values, it would match up for all real numbers. Isn't that? For e to the x, yeah, x to the n of 1 factor. Correct. No specific. Yes, it converges for all real numbers. So you guys see that will converge for all real numbers? Everybody good with that? Aren't you astounded and amazed? Hey, in Zoom, are you even there?
I'm here.
Are you astounded? Are you astounded and amazed?
Yeah.
Good. Excellent. All right. Let's see if you guys can construct a 6th order Taylor polynomial for cosine and then the Taylor series for cosine. I'll have you guys do this one on your own. So I'll pause our recording here for a second. And then did I go back to did I share the screen again? Am I off of Desmos?
Yeah.
Yeah, okay. All right, cool. I'll give you guys, I don't know, 3 or 4 minutes, see if you can come up with one for this. All right, so what did we do? We had cosine of 0 first, right? Which was 1. We had negative sine of 0, which was 0. We had negative cosine of 0, which was negative 1. This is our first derivative, our second derivative. Then we had a positive sign, that was 0, third derivative, cosine 0, fourth derivative. Back to 1, fifth derivative is 0, sixth derivative is going to be back to negative 1. Everybody agree with that? Right. Luckily, sine and cosine, the derivatives repeat every 4 times. So first term should have been a what? Should be 1x to the 0 over 0 factorial, which should be 1. Next term, let's see, would be x to the first from the 0 term, but we can ignore that one, right? And then this, so we should get a minus x squared over 2 factorial. And then our x cubed term should have been 0, but our x to the 4th term should have been plus x to the 4th over 4 factorial. Our x to the 5th term should have been 0, and our x to the 6th term should have been minus x to the 6th over 6 factorial. Everybody agree with that? Derek, you good with that? People at home good with that?
Yep.
All right. And what was our summation? Our sum from n equals 0 to infinity of? Again, oscillating, so negative 1 to the n. X to the 2n. I think just 2n, right? Because the first term should be x to the 0 still. We don't want a plus 1, so it should be x to the 2n. That gives us x to the 0. Then when n equals 1, it gives us x squared. When n equals 2, it gives us x to the 4th. And then the same thing in the denominator, 2n factorial. And be careful about how you write that. Make sure that 2n is in parentheses in your factorial. Because if you don't put it in the parentheses, that means 2 times n factorial. The n factorial takes precedence over the multiplying by 2. You need a different value. Good? Everybody agree that that series seems right? What do you think that one converges for? All real numbers. In fact, both of them, both sine x and cosine x, don't just converge for all real numbers, they actually converge for all complex numbers as well, which is something of interest that we will look at some point. Cool. Any issues there? Everybody good with that? All right. So I don't think I had a page up that had like the general form. This is the general form for your Taylor series at x equals 0, which we also call the Maclaurin series. It's just f of 0, f prime of 0 times x, f double prime of 0 times x squared over 2 factorial. I think I wrote this out for you the other day, maybe. But I don't know. If you want to write it down here, here it is. Otherwise, we'll continue on. That's just our general form. And this will work for any function. Any function you want to find a series for, you can apply it here. You can come up with a Taylor polynomial for it. Sound good to everybody? I'm going to give you guys time to write it down until I see that the people that are writing it down here in class are done writing it down. Y'all have a good weekend there in Zoom? Cool.
Relaxing.
Relaxing. Wonderful. Wonderful. Y'all good here? You guys at home ready then? Uh-huh. You write it. Oh, can you write it like this? Like k equals 0 to 9? Yeah. No, they want to have it. They want to see all the terms right now. All right, let's see if we can do this one real quick. I think you guys should be able to do this on your own. I think. Whatever, we'll do it together. So fourth order Taylor polynomial for y equals cosine 2x around x equals 0. So first off, what's the cosine of 0? Okay. Our first derivative should be negative 2 sine 2x, which at 0 will be zero. Our second derivative will be negative 4 cosine 2x, which at 0 will be negative 4. Our third derivative will be 8 sine 2x, which at 0 will be 0. And our fourth derivative will be 16 cosine 2x, which will be 16. And so this time we've got some different coefficients here, but we can still write out our polynomial. It should be 1, it should be minus 4x squared over 2 factorial, and it should be plus 16x to the 4th over 4 factorial. And what does that simplify down to? 1 minus 2x squared plus what? (16 over 12, right? Should be 2/3 x to the 4th. And that's the fourth order Taylor polynomial. So we can do it with any function we want. And you note that, and this is something we'll talk more about later, if we took the series for cosine, we took the Taylor polynomial for cosine, and we just replaced all the x's with 2 x's, this is exactly what you would get. we'd get the exact same thing. So sort of like we did with the 1 over 1 minus x, where we just replace the x with like a 2x or with a negative x to write a new series. Same thing works with Taylor series. You just throw a 2x in there instead of the x to your series for cosine, right? If I threw a 2x in here, we would have had 4x squared over 2 factorial. And here we would have had 16x to the 4th over 4 factorial, which is exactly what we had here. So it works out exactly the same. Everybody see that? Okay, cool. So if we want to generate a Taylor polynomial around some other value, not 0, some x value equaling to a, we're going to use literally the exact same formula, except instead of just doing f of 0, f prime of 0, f double prime of 0, we're going to do f of a, f prime of a, f double prime of a. And instead of x to the 0, x to the 1, x to the second, we're going to do x minus a to the 0, x minus a to the first, x minus a to the second. And that will give you a Taylor series generated at any x value that you want. And once again, as soon as we move it away from 0, it is no longer called a Maclaurin series. It's just called a Taylor series at that point. They may refer to it at 0 as a Taylor series at 0 or as a Maclaurin series. But you know, if they call it a Maclaurin series, it has to be at 0. And if they don't call it a Maclaurin series, it could be anywhere. So hopefully that's pretty straightforward. I mean, it looks the same, I think, as the other one that we did. So I'll give you guys a minute or two to write that down if you wish, and then we'll move forward and do one of these. I believe the AP test is 2 weeks from today for those of you with the May 4th date. We changed it. Okay. Wonderful. It's probably best. Yeah. Who's still on May 4th? Oh, in the chat. Kevin. Anybody else May 4th? No? All right, so let's see if we can do this. Were you guys done with that, Jen? Are you still right? You're good? All right, let's see if we can do this. Let's find a Taylor series for e to the x at x equals 2. So first thing we need to do is we need to find what? What do we need to find first? Yeah, let's find f of 2. So what's f of 2? It should just be e to the second, right? What about f prime of 2? That's just going to be also e to the second. What about f double prime of 2? That's also going to be e to the second, and so on, right? These are all just going to be e squareds as we go through. Would you all agree with that? Yep. Okay. So what is our first term going to be in the series? Should be e squared x to the 0 over 0 factorial, or just e squared. Next term should be e squared x minus 2 over 1 factorial. And then it should be e squared times x minus 2 squared over 2 factorial. And e squared times x minus 2 to the 3rd over 3 factorial, and so on. So what does the series itself look like? The sum from n equals 0 to infinity of e squared, those are the same every time, x minus 2 to the n over n factorial. And we could show this on Desmos and just show that it looks really good right at 2. And the larger number of the upper limit of our summation there, the larger upper index there for n goes, the more it's going to look like it surrounding 2. Good? Y'all here good? People at home, are you good with that?
Yeah.
Wonderful. All right, now here's a fun one. All right, this is just easy and fun for us to do. It's not going to be fun, but let's find the third order Taylor polynomial for this function at 0. How would we do that? All right, we're going to find all of the f of 0 and f first, second, and third derivative at 0. And then we should be able to write it out. And we would hopefully note, what would we expect the answer to this be? Well, I mean, the final answer. I mean, what would we expect the final answer to be? We're writing a polynomial to represent this polynomial function. What would we expect the answer should come out to be? The hope would be that it will come out to be the exact same polynomial, right? That's just, going way back to what we did the very first time. So what's f of 0? Let's just see if that's true. F of 0 is f prime of 0 should just be this coefficient, right? It's just that 4. What about f double prime of 0? Right, so if we go through, if we're taking our derivatives here, we're going to end up with not a -3. We should end up with -6, right? Because we are taking the derivative. As we go down here, this becomes 6x squared minus 6x plus 4, right? And this becomes 12x minus 6, and then this becomes 12. So what's our third derivative? Should be 12. Everybody good with that? People at home good with that?
Yeah.
Okay. And so as we go through, we'll note that if we simplify this down, 6 over 2 gives us that 3. And 12 over 6 gives us that 2. And we end up with the exact same polynomial that we started with. Right? So if you ever asked to find the, let's say, third order Taylor polynomial for a third degree polynomial, you will know that at x equals 0, it's the exact same polynomial. What if I shifted it away from x equals 0, though? Would that change things? I don't know. Let's take a look. Let's see if that changes anything. It's going to make our arithmetic a little bit more annoying to figure out because we're looking at 1 now instead of 0. But we're going to have those same derivatives, right? What are our derivatives? They are 6x squared minus 6x plus 4. They're 12x minus 6, and then 12. So what's f of 1? No. Anybody? What's f of 1? -2. What's f prime of 1? What's f double prime of 1? And f triple prime of 1. Everybody agree with those? Yeah? No? Maybe? Okay. So if we were to write this out, we'd have -2. Well, that doesn't look like a -5, does it? No. -2 plus 4 times x minus 1, right? Plus 6 times x minus 1 squared over 2 factorial. And then plus 12 times x minus 1 cubed over 3 factorial. And so if we were to simplify all of this out, do you guys think it would come back to be the same polynomial? Derek says no. Noah says yes. Jenna looks quizzically at me. And everybody in Zoom stays as silent as they possibly can. Let's find out. We have -2 plus 4x minus 4. This is a 3, right? So we're going to have plus 3 times x minus 1 squared. So that'd be plus 3x squared. And then minus a 6x. And then that's going to be a plus 1. So times 3 is plus 3. And then here we're going to have 2 times x minus 1 cubed. We should know what x minus 1 cubed looks like, right? That should start off with an x cubed, so 2x cubed. And then it should be minus 3x squared. So if we multiply that by 2, that's minus 6x squared. And then it should be plus 3x, so that'll become a plus 6x when we multiply by the 2. And then a minus 1 at the end, which when we multiply by 2 should become a minus 2. And let's look at our constants. Negative 2 minus 4 is negative 6. Plus 3 is negative 3 minus 2 is negative 5. That seems good. We got a 4x minus a 6x, that's negative 2x, plus another 6x, that's a plus 4x. We got a 3x squared and a minus 6x squared, that's a minus 3x squared. And we've got a 2x cubed. And it comes out to be exactly the same. So anytime you are asked to construct a Taylor polynomial, small chance this might happen. For a polynomial, as long as they're the same degree, it will be the same function. Exact same function. No matter what x value you plug in. If we did this at x equals 2 or x equals 100 and simplified it out, we would get the exact same original polynomial. Everybody good? If you ask for a 5th degree Taylor polynomial for this function, yeah, it'd still be the same. If they asked you for a 2nd degree one, it would not be. Right. If it's the same degree or higher, it's the exact same. They would most likely not ask that in a free response. They might ask it in a multiple choice. All right, now, this is something that I briefly mentioned. You probably don't need to necessarily read all of this. So I'm just going to tell you what you can do. Just like when we did with the 1 over 1 minus x and we replaced it with a 2x. We already talked a little bit about this. I replaced the x with a 2x to get a series for 1 over 1 minus 2x, or we replaced the x with a negative x to get the series for 1 over 1 plus x. You can do the same thing, like I said before, with Taylor series. So if I wanted to figure out what the Taylor series for 1 plus cosine 2x over 2 would be, I should just go to take the series for cosine 2x, add 1 to it, and then divide it by 2. Right? And that would give me the series for 1 plus cosine 2x over 2. Or I could do that in any manipulation with any series that I already knew. And speaking of that, the series for sine x and cosine x, you need to memorize those. Those are another 2 you need to memorize. Everybody good with that? So that's the whole idea here. Is I can manipulate them in any way I want. I can multiply them by anything. I can multiply them by a constant. I can multiply them by a variable like x. I can get x sine x by just taking sine x and multiplying it by x. I could take the series for sine and the series for cosine and add them together to get the series for sine plus cosine. So you can basically do any of your regular old operations with these. So we'll practice one of these real quick, and then we're going to do another one that's even cooler, and then we'll probably be done for the day. So let's find a series to represent e to the 2x minus 1 over 3, and then let's figure out what the interval of convergence for it should be. We're just going to use this method that we were just talking about there. So what's the series for just e to the x? Let's start with that. Right, so what is it? It was like 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on, x to the n over n factorial. Everybody good there? So to turn that into e to the 2x, that ought to look like, well, I just replace all of the x's with 2 x's. So 1 plus 2x plus 2x, the quantity 2x squared over 2 factorial. plus the quantity 2x to the n over n factorial. Everybody good with that? All right. What if I want to subtract 1, though? Subtract 1. So what does my series now look like? Do I subtract 1 from each term? No. I have one side of the equal sign, the other side of the equal sign. If I subtract 1 from this side, I subtract 1 from this side of the equal sign, right? This is something I'm trying to like make my 12-year-old son understand, that you don't subtract it from every single thing over here. You just subtract it from the side. So this just becomes 2x plus 2x squared over 2 factorial, and so on and so on and so on, 2x to the n over n factorial. So before we divide by the 3, let's go back up here. What is this series? This is the sum from n equals 0 to infinity of x to the n over n factorial. Agreed? What is this one? The sum from n equals 0 to infinity of 2x to the n over n factorial. True? What about this one? Sum from n equals 1 to infinity of 2x to the n over n factorial. Everybody good with that? So we've shifted, we got rid of that first term, so we shifted our index up by 1. Yeah. Good? Cool. If we wanted to leave our index at 0, we could have shifted these up to be n plus 1s if we wanted to. So we could have left it at 0 and then made it n plus 1, n plus 1 factorial. Everybody good there? People in Zoom, are you good there?
Yep.
All right. And then if we want to divide it by 3, we just divide it by 3. 2/3 x plus 2x squared over 2 factorial times 3. And so on. 2x to the n over 3 times n factorial. Note that the n factorial is in parentheses with a 3 outside of it, not a 3n factorial. And this would be yeah, you're right. Okay, never mind. Yeah. You're right. I'm gonna write it with the parentheses. Everybody good with that? Okay. Cool. Next thing, let's see, that's the end of this, but we're gonna do something else with this. So we've now, I believe, we've talked about all of the different series that I need you to memorize. So if you look in the Google Drive, you will find a list in there that says like series to know or something like that in the other documents folder of the Google Drive. There's a list of them. The list includes 1 over 1 minus x. I believe it includes 1 over 1 plus x. It will include inverse tangent, natural log 1 plus x, e to the x, sine x, and cosine x. So those, I believe it's 7. There are 7 of them that I want you to for sure have memorized. Inverse tangent, natural log 1 plus x, sine x, cosine x, e to the x, 1 over 1 minus x, 1 over 1 plus x. Yeah, that sounds right. Okay, cool. All right, now let's do something cool using this same idea where we can manipulate these functions in any way we want. We know the series for e to the x. True? What is the series? We just did it, right? What's the series for e to the x? Should be the sum from n equals 0 to infinity of x to the n over n factorial, right? One of the ones you need to memorize. Everybody good there? Now, I think I said before that this converges for all real numbers, and I think I might have added, it also converges for all complex numbers. Remember when I said that? Okay. Everybody at home remember when I said that?
Yes.
Wonderful. All right. So let's take a look and see if we can figure out what the series for e to the I, our imaginary unit, times x should look like. should be a sum from n equals 0 to infinity of, well, instead of x to the n, it should be ix to the n over n factorial. Do you all agree with that? Everybody agree there? Yeah. And let's write that out. What does that look like? What's the first term? At n equals 0, that should be anything to the 0 is 1. So what's our first term going to be? Just a 1. And then when n equals 1, we're going to get plus ix. Yeah, I don't need the over factorial. It's fine. When n equals 2, this should become x squared, and it should become what? Yeah, it should become a minus because we'll have I squared. Remember, I squared is -1, right? I is the square root of -1, so I squared is -1. So we're getting a minus x squared over 2 factorial. So no imaginary unit in that one, right? What about the next one when n equals 3? Yeah, I cubed is what? It's I squared times I, right? I squared is -1, so that's going to give us another minus. And then it's going to be minus I x cubed over 3 factorial. Do y'all agree with that? What about the next term? That's going to be I to the 4th. What's I to the 4th? It's I squared times I squared, right? So it's +1. So we're going to end up with x to the 4th over 4 factorial. And from there on out, those i's and negative i's and positive i's and all that are just going to repeat in the same order, aren't they? Right, so if I do x to the 5th, that's I to the 4th, which we already just said was 1 times I. So we're going to end up with plus I x to the 5th over 5 factorial. And what should the next one be? Sort of running out of room here, but we'll say minus x to the 6th over 6 factorial. And then it should be a minus I x to the 7th over 7 factorial, and so on. Everybody good with that? Okay, cool. Everybody at home good with that?
Yeah.
Okay. Now, some of these terms have imaginary units in them, and some of these terms do not have imaginary units. What we're going to do is we're going to go back to this rule where I was like, all right, sine x plus cosine x is the sum of the series for these. Well, what I'm going to do is I'm going to split this into 2 different series. I'm going to split it into one series that has an imaginary unit attached to it and one series that does not have an imaginary unit. So my first series is just going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on, plus dot, 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 forever. And then I'm going to say plus, and then I've got this ix and this ix cubed and this ix to the 5th. Can I factor an I out of all of that? I times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. Everybody okay with that? All right, cool. What is this series on the left? This is cosine of x. So on the left, we've got the sum from n equals 0 to, I'm going to write out the series, -1 to the n, x to the 2n over 2n factorial. And on the right, we had what series? We had sine x, right, which was sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial times an I. And they all have an I, so I'm just going to put that I out in front. And like we just said a second ago, somebody just said that this first series is cosine x, and this series is I sine x. Everybody good with that? Everybody agree with that? People at home in Zoom, are you okay? Yes, those also converge for all rooms. True. That is true. So here's what we've done. We've said e to the ix is equal to cosine x plus I sine x. Everybody agree with that? Okay. So what we're now going to do is, since we know that this converges, right, e to the x, any series for e to the x or e to the ix for that matter, converges for all real numbers and for all imaginary numbers. We'll just say for all x, okay? Converges for all x. Let's evaluate this at x equals, what are we going to evaluate it at? X equals, no, pi. We're going to evaluate this at x equals pi. And so that will give us e to the I pi equals cosine pi plus I sine pi, which will tell us that e to the I pi equals, what's the cosine of pi? -1. And what's the sine of pi? 0 times anything is 0. Or effectively, what's known as Euler's identity, e to the I pi plus 1 equals 0. The single most beautiful mathematical expression ever invented. Good or no? Yeah? Wonderful. What else? I think that's a good place to stop for today. What do we think? I think I mentioned this thing to you guys all last year, right? But no, we never talked about this last year. No, very sad. Yeah. Why is it important? Oh, so many reasons, David. So many reasons. It basically, I mean, it lets you overlap all the stuff on the complex plane with stuff in the real plane. It's super important with vectors and dealing with vectors, all kinds of fun stuff. We good? Good place to be done. All right, we stop.